My name is Mehmet Öner Yalcin. So I'm DevOps Network Planner at Sky and in the analytics and planning team. So it's this title tells a bit like kind of I'm doing a little bit of systems, a little bit of network engineering, and actually my background is network engineering, and also a bit of data analysis I do for like performance measurements and like those kind of things. It's like a little bit of data science stuff, but it's mostly network related. And so I'm spending most of my time in between all these three tasks, and I also do the network automation a bit. Maybe it's going to be another talk at another later time, but today I want to talk about like how we measure the performance, and this is more like a little bit more system side of things. And I enjoy coding in R and Python and SQL. So. Yeah, as I said, this talk is not exactly about network devices. It's about networks, but it's a bit of network, like foundations, like again, like measurement, like pings and all those stuff, network packets, and how we organize these things to build something more structural, more automated system that we can get more information. We created some tool called Hubble, and this is Edwin Hubble, who is a great astronomer, American astronomer, who for example, discovered the universe expanding, and also found out that, for example, there are other galaxies, and like it's not just only Milky Way galaxy here. And this is the Hubble Space Telescope, which obviously takes name from the Edwin Hubble, and that's actually calculates the speed of expanding of the universe after Edwin Hubble discovered this one many years later. So I took this one as the name because this is pretty much what we're trying to do. It's like, for example, Hubble Space Telescope has some equipment, different equipments that just you can target to one part of space and get measurements, or you just have other equipments that you can get more general measurements and less resolution. So it's pretty much like that way. This our tool. And this is a kind of more, at the moment, it's a network layer measurement tool, but we are thinking to expand it to other layers. So what it does is that it just concurrently measures different transit providers, and so it measures the quality of those transit providers like for longer periods of time. And but also it does, apart from just like network layer measurement, it enriches this data with things like BGP, geolocation, so that you can correlate this information when you get the data back. And one of the things is that it does, you can obviously feed something static, but also it does the automatic host discovery, so that with automatic host discovery you don't need to worry about like exactly which end host you need to ping about. It's just that scans that IP space and then flies out. And we try to make it more scalable, so that because basically measuring transit provider means that you're measuring quite a bit of things. It's a Python library, but it's a thin wrapper around a couple of tools that I'm going to explain in the next slides. And in the backend, as a data storage, computation, and visualization, it uses Elasticsearch EIT stack. So it's like Elasticsearch as a computation platform, and Logstash as data ingest, and the Kubernetes for the visualization. And so how we came up with Hubble was that we had a couple of transit providers, and as a network analytics team and planning team, we were asked from the finance guys saying that we were going to negotiate with these transit providers, but give us some concrete data. We want to understand which one is performing better, or just should we go for this one because that they're telling that they're good and they're a bit more expensive, but is that true? So and we know that the transit providers has different presence, so they have different footprints all over the world. So not all of them are the same. And one of the things is that we need to measure from Sky's perspective. So it's because the users are getting the traffic, Sky users or any our users from certain areas. So we need to understand. We're just measuring all those ones. And so we created this tool to address this problem. So basically, it just gets the subnets of interest, which I'm going to explain, and scans the host and finds the host there, and then in the subnets, and then measures the performance. And now we are also targeting, expanding this one for other specific measurements across Europe, because Sky is a European media company, so we got presence in other countries like Germany, Italy, and Austria. So one of the problems, the biggest problem when we came up was like when my boss said, like saying, we need to measure the transit providers, and I said, well, transit providers basically means the whole internet, so how can we do that one? So, and there are now, I think it's around 700,000 routes, and that's not really very feasible. But something we know that not all the subnets are sending us the equal amount of traffic, so it's not like some uniform distribution. It's something this is called like Zipf's law here. So you might just think like, for example, there are a couple of big cities all over the world, and there are more number of cities, medium size, and much more small size. So similarly, like just only there are few subnets sending lots of traffic, or you're sending lots of traffic to those subnets, and most of the subnets you're exchanging almost minimal traffic. So identifying these subnets is just solving most of the problem, just to target where you want to measure. So we use the tools like NetFlow to understand which subnets are sending us the most traffic from our transit providers. And we were using like Arbor and Kentic, and they have APIs, so we can query them and get lots of information from those APIs. And Hubble exactly doing this one, and also it takes static files. For example, if you want to measure something somewhere else, which I'm going to come later. Once we bring down the problem size from 700,000 K routes to 500 routes only, and we just what we do that solves one of the problems. But there is another problem, is that we want to measure the transit provider performance, but the routing is done on the destination base. So you want to send the traffic to one transit provider, but if you just leave it to the normal routing table, it may go in with another transit provider. So this is one of the, we need to solve this problem. So what we did is like on the peer transit provider routers, like the edge routers, we did the source routing. So it's just like we force the, for example, a prober wants to measure transit provider 1, so that the source routing exactly ensures that the outgoing traffic is going to go through the transit provider 1. This is solving half of this routing problem. Then another one is that incoming traffic, obviously. So what we did is like we just put the prober for transit provider 1 in one public subnet /24, so it's like BGP internet routable. So we just advertise exactly this route, here also shows, through this transit provider. So incoming traffic is for this prober is going to come back from this transit provider. So that solves both together with source routing. We ensure that the traffic always goes through the intended transit provider. Well, in one of the cases, this is I say the soft requirement in the slides because you might just, because you might not have /24 enough, it's just quite expensive. What you can do is that you can, all of the three probers can reside in the same public space, could be much smaller than /24, and then you can just enforce the source routing to go out, but if you just advertise only all these, if I'm assuming all these probers in the same subnet, if you advertise through one transit provider, they are going to come through the one transit provider. So it's just only difference is that their outgoing path is different, but incoming path is going to be the exact. So you can still make good measurements. So that's I say, soft requirements. So one of the system requirements from was that the target selection. So we wanted to make sure that it's automatic, as I expressed previously. So we shouldn't interfere. So what the routes important for Sky should be chosen automatically. And scaling is that. So we might need to really scale a lot. So if there are thousands of hosts or maybe millions of hosts, we need to scale very quickly. So and it has to be horizontal scalable. Each component can be deployed a couple of in parallel. And so in microservices here is just each component needs to be independent of each other, so that they're loosely coupled. So they deploying or just development of one module shouldn't affect another one, and all the information exchange between those modules should be done through a message bus. Like we use the RabbitMQ, but you can use anything else. Obviously, so it's just like the modules are sending traffic. So one of them is publishing, another one is subscribing. So this is how we achieve that one. And the development, each component should be treated as a plugin. So you can add, for example, today we just have only the layer 3, like network layer like we can measure that one, but you can add, for example, TCP scene. You want to send TCP, you want to discover a TCP host that is responding to TCP queries, and then you can send the TCP scene messages. So that should be you should be able to develop that one very easily, and shouldn't be dealing with the other stack or software stack. And the enrichment is really important because we want to not just to get the ping data back, but we want to understand a couple of things like where it comes from, the ASN, for example, and the geolocation. And if you want to add more information, you can add it to this one. And data analysis, this should be like, there are lots of data coming back, but you need to be easily parse this information and visualize, and then obviously also send to another system if you need. So this is where it comes to like Elastic Stack, which I'm going to explain in the next slides. This is like subnet ingest. Hubble just talks to APIs, like the Arbor and the Cantic API to understand the subnets of interest, and gets from there, and then it puts into a message bus, and those subnets are sent to something called ZMAP. And these guys, this is an open source project, and kudos to ZMAP guys. They create a very nice scanner. You can think of it's like an NMAP, like the network scanning module, but it's the internet scale one. So it's very fast and it's very lightweight. And they have a couple of more projects here. If you're interested, just go into this website and you will get lots of interesting information. And for the moment, it's just ICMP and TCP scene scans supported by Hubble, but ZMAP scanner itself has more features. So, and just like we try to make sure that our scanning is not like a DDoS attack. So it's just we try to follow the best practices. For example, if people doesn't want to be scanned, then we have a website on where the probes are being sent. They can contact us from there. So this is a very small piece of code, like how if you want to see how the Hubble works, it's just like you import the ZMAP and you specify the prefix, for example, and then you just say scan, and I want to get only, this is /13, but I want to get only maximum 50 results. So you just, once you get it, just return back me the whole list. And I want to use just only 1 megabit of bandwidth. You can go up to 10 gigs, I guess, and it's, you can scan really fast. So it returns you back all the ICMP responding hosts here. And so prober, so once the ZMAP returns back all the responding hosts, then it sends through the message bus to something called Scamper. Scamper is like an open source platform product by Center of Applied Internet Data Analysis in University of San Diego. So this is also wonderful, another small tool. It supports quite a lot of features. For the moment, I'm just only exploiting the ICMP ping, but you can use almost lots of interesting features from this tool. So this is good because it just does parallel pinging, for example, parallel measurements, and it's scalable. But it's not really like you cannot go up to 10,000 hosts scanning at the same time. At least my experience. So I did some more parallel scanning. I will explain it later. But one of the things that this tool returns back is like structured data. Like for example, if you import Scamper and then you just make a label here in this one, like just because it adds into the JSON file, JSON blob returns back. So you know that which transit provider you're using, you're probing, and then like these hosts are like 50 hosts, for example, or more hosts, and you just specify the other parameters. And it may return back you this kind of structured data, and so if you see the general statistics down there, but you also see something interesting there. Like normally Scamper doesn't return back, but this Hubble Scamper returns back you, for example, ASIN information. So that's one of the enrichments. So also you add like the provider tag over there. If you prefer to do more like data analysis just on this tool, you can return back as like kind of pandas data frame. So each measurement is a row of pandas data frame, so that you can do something more interesting analysis if you just want to play around. And the enrichers, like if you remember that ASN tag is actually coming from another Python library called PyASN. It's developed by the TU Delft University in the Netherlands. And it's very, very fast IP to ASN lookup library, really pretty fast. And so I use that one to add the ASN information. There is also like the BGP information you might attach, but that's something I haven't, it's not shown here because it's more like, depends on the, like Arbor API, for example, I was using that. But in general, like it's not it's something you might need to get it from somewhere else, maybe if you want that BGP information. The log stash module from the Elasticsearch stack, that also has the geo tag for the each scan. So that's now you have the country-wise or geography-wise or city-wise information. And all the data is saved to Elasticsearch. It's a NoSQL database, and that's pretty fast and also very easy to expand. Very easy to horizontally scale that one. You just add more clusters and that's it. So and it also comes with that Elastic stack. You can add also Kibana, which is data visualization, and it's very simple visualization platform, and also very powerful. That you can just look the data from different aspects and ask different many queries. So that really helps to understand what you're measuring actually. And yeah, as I said, like RabbitMQ we use for message bus. So for example, let's say maybe if there's So here, for example, the subnet getter is just like we get the subnets, and the RabbitMQ sends a ZMap and RabbitMQ, and it's also like, for example, here in the right hand corner, it's just like it multiplies. I mean, like it's just sends each packet triple times to Scamper. So it's just each RabbitMQ is just doing not just only publishing and subscribing, but also like making sure the load balancing. For example, there are multiple Scampers running for transit provider 1. So let's say there are 10 hosts are coming, then each of the, let's say there are 5 of them, 5 of the transit provider probers, Scamper probers there. So each prober is going to get 2 of the hosts. So RabbitMQ solves lots of like scaling problem as well. Yeah. So this is like a kind of how I deployed it initially, but just to be just to explain further, you might put these all kind of components completely separate on different hosts, virtual or physical hosts. Just want to make sure that you at least have 3 Scampers, or if you have 3 transit providers here, then you need to have 3 Scamper instances. Just make sure that they're getting measurements. But all of them, all other components can be staying anywhere else. Elasticsearch cluster is just like you see here. 3 of the hosts are creating one big Elasticsearch cluster, which is like performing better, obviously, because it's scaling. And so this is probably people from the back you cannot see very well, but I'll open up a live one. So this is a general view of a dashboard. So here's, for example, you see the median like kind of round trip time or the jitter, or like also you see that which country is like has the most jitter or package loss. Is the standard deviation, yeah. So that's the jitter, or like Lithuania at that point had the highest jitter. And if you look at that kind of package loss, you can see all those ones there as well. And this is the timeline shows you how it progresses during the day. And if you see, like for example, this orange line is slightly better for medium RTT. This is, for example, they're very close, but in general, like that's provided, which is like level 3 at this point, is slightly better. But if you ask questions like, I want to look at by country, like for example, China, and then you see like there is like 300 round trip time for medium for level 3, but NTT and GTT has better, almost like 100 milliseconds better. And you see also standard deviation, like the jitter changes during the day. So you might need to understand if there's any congestion happening only one transit provider, you would easily understand. And you can ask, of course, lots of different questions, not just country, but like ISP level, ISN level, or like let's say continent level if you were interested. Yeah, by transit provider, you can only show one transit provider, obviously. And one of the things we discovered, for example, we didn't know about it, is just like Limelight. Limelight is a content delivery platform. And when we look at this Limelight graphic, we just noticed that like the level 3 has around 12 milliseconds of round trip time, but GTT and NTT has like around 18 milliseconds, and 18 milliseconds is telling us like something really interesting going on. And once you run the trace route, by the way, one of the next things I wanted to add is the trace route, so that we can not just run into from the command line, but we have a visualization of those ones. So it's like, if you see here, GTT, the sixth one is still in London, but the seventh step is going to New York City and connecting to, going to Limelight and coming back to Frankfurt, London and Frankfurt. So basically, in order to get the content from Limelight, you need to first cross the Atlantic and come back to Europe again. So that's why GTT is like having that much of round trip time. And obviously, when you look at the NTT is just going to GTT, connecting to GTT, and obviously GTT again goes to across the Atlantic and comes back to Europe. In the case of like level 3, it just connects to Cogent. So Cogent is then directly connecting to Limelight. So and it's staying in the Europe. So if you see, it's just like around Frankfurt, and I think CDG is Paris, I guess. So before limitations, I will maybe after limitations, maybe I'll just briefly show the live version. Yeah, at the moment it's just doing the layer 3 probing. And there is no support for IB version 6 yet, but it's just like because I didn't have very much time to spend on this project after I deploy. And it's at the moment it's just a thin wrapper around all these tools. So it's basically force a new Unix process and then calls this scamper or like the ZMap. This is how one of the ways I parallelize the scale the whole platform in a single for example prober. Obviously you can have multiple probers for the same transit provider. That's one of the scaling. But I think I need a better integration. Like if I'm not good at C, but if I learn a bit more C, then I can. Or if somebody comes and puts like integrates with this C library of those measurement tools, that would be even better. Yeah, one of the things is that pings and trace route and all those things are blocking processes. So it's like when you send a ping, you just wait until it returns back. So you need to parallelize. So what I did, one of the things is that I use monkey patching from this Python, this general library. That replaces the sub-process module in Python with a kind of non-blocking one. Well, there are some improvements can be done by using the native support from Python 3. Python 3 has a async IO module, which I haven't used. That's one of the improvements can be done. And for the moment, the installation is slightly tricky, not really very tricky, but just like I need to containerize the application so that everybody can very easily deploy. Maybe you have the question like, is it open source? Yes, it's going to be open source. Just I need to refactor the code a bit, and as I said, like make it a little bit more user friendly, and then I will open source this one. Yeah, this is, for example, a running instance. Like this is not taking the measurement from all over the world. This is a targeted measurement. Sorry. Let me have a look. So this is the Kibana interface. So it's, for example, here it's just between 24th and 27th is chosen, but you can choose any time. And there was 22 million of measurements at that point. So if you look at it, it's just like each single measurement is like, as I said, it has when Logstash is sending this ping data, it also has the geolocation information meta tag. So it's like, for example, this is German, and it's actually all the packets here are targets for Germany, and it's measured through the GTT, and then you see other information as well. So let me go for the dashboard. This is running in the lab, and running on not really very powerful machines, so it might take a little bit while to parse this data. So this is the ASN, one of the ASNs that we're targeting. So basically we are taking, because Sky also has a footprint in Germany, we are doing some constant measurements for some analysis. So this is one of the ISPs that we have customers, subscribers watching the video stream. If you look at here, so for example, this much of unique host targeted, and mean like the package loss and packet loss, and you see, for example, some interesting events are happening, like around the evening time, like the whole round trip time and the jitter is increasing, and you might see like it's mostly all these providers are very close, but this is just the case for this particular ASN. But if I just go for example, let me just go for Telefonica Germany, for example, if I remember correctly. Sorry. This filter is running now. Yeah, so this is Telefonica Germany, and here you see, for example, level 3, around the median. If you look at the median, jitter is just like has larger peak, but you might want to look at like 95 percentile, which might give you more information about like only the 5% of the subscribers experiencing worse than this jitter. So still, level 3 has some problems. And when you look at the RTT, round trip time for 95 percentile, there are mostly entities staying fine, but GTT and level 3 has some problems for this ISP. But if you look at other ISPs, all of them behaving different. So that gives us a kind of granularity in the ISP level, or time, or even like your location. Like if you want to look at target Berlin, but not Frankfurt, then you can choose that one as well. So I think that's pretty much. And we also, I would say also we are looking for teammates. If you are interested, just let us know. And if you have any questions, I'll be happy to take.
Questions?
Oh, sorry. So does Kibana handle all the statistics for you?
Yeah, you can.
Okay.
Yeah, you can create these ones.
Sorry.
Yeah.
Okay.
Yes, Kibana has all these statistics, and you can really easily create all these ones from the data. Like it takes about less than half an hour to create all these ones in the dashboard. So it's very, very intuitive, and you don't need to code from the Kibana. I mean, you can code, but as you see, there was like some queries running there. But you can just point and click and choose the data source, and then you want to say, okay, the x-axis should be this one, and I want to like to chop it by this one, and then you will get very easily. Like it's pretty straightforward.
How are you integrating your alarming layer? Are you using XPack within that, or are you using a separate client outside of Elk?
This was more like a kind of more research project, so we haven't integrated anything yet. Just more like at the moment it's just taking measurements, and we're trying to build more confidence on this platform. And once we are happy, yes, we are thinking to like use this one as a kind of performance-based traffic engineering. But still, we are just trying to understand this one really creates some good signals. So it's going to be decided maybe later.
One more question? Nope.
Thank you very much.